So let's do a brief recap. So, the angular momentum algebra. Okay, before we do a recap, there is a useful identity that I want you guys to think about. If you have an epsilon tensor, Eijk, and you have another epsilon tensor, Lmk, so you're summing over k. K is a repeated index, okay? So this is going to be equal to delta I L delta Jm minus delta Im delta JL. Okay, so this is a very useful identity. Okay, so that comes whenever you're doing angular momentum stuff, you might want to use this. Okay, so let's start with the angular momentum algebra again. Ji and Jj. The commutator is I epsilon I jk, where we are using units in which h bar is 1. Okay, so if h bar weren't 1, there would be a factor of h bar on the right-hand side. So the total angular momentum algebra that's given by j squared, and that's j1 squared plus j2 squared plus j3 squared. That commutes. And so then we define j plus and j minus, and so this j squared has a name. It's called the quadratic Casimir operator. Okay. So see that it's a nonlinear operator, nonlinear combination of j's. It's not a nonlinear operator. It is linear on Hilbert space, but it's a nonlinear combination of the generators of the algebra. Okay. And so we have essentially, and you might say, okay, if you're like Nahi or somebody, you might say, why aren't we discussing j cubed, right? Because we could create an infinite number of operators. Why are we only saying, oh, the set that is relevant consists of j squared, j1, j plus, j minus, right? Or j1, j1, j2, j3. Can someone tell me why this is not the case? What if I take j squared times the scale, because times j, right? And the fact is, this is actually on this space, it's actually proportional to the identity operator. That is the reason. So if you multiply it by, say, another j, you get something proportional to these guys. You don't get a new operator.
So it's the same thing, just the...
You're right, so it's the same thing. If you had a bigger Lie algebra, you could have more quadratics, but here, the cube, like this, it doesn't give you a new operator because this actually is, on this Hilbert space, it's proportional to the identity. And how do we know this? Well, we know this intuitively because we can see that all the states have the same, eigenvalue, right? And also because we have something called Schur's lemma. And Schur's lemma, which is proved in linear algebra courses and also in group theory courses, Schur's lemma tells us that if we have a set of, commuting, if we have a set of operators and there is a particular operator which commutes with all the other operators, then that particular operator must be proportional to the identity operator, which is what J squared is.
Is it
And
like the center of a group that we talk about in group theory, that it forms a cyclic group with
it is similar, but it is not a center of a group, because J squared should not be thought of as being a generator of the group. The J's are, but the J squared isn't a generator of the group. Okay? So it would be a center if amongst these guys, there was some, some